Hello, I'm William Day and this is my speaker identification project using music information retrieval techniques. The main objective of this project was to create a streamlined system to identify individual speakers from audio samples using advanced music information retrieval methodologies. The process began by segmenting audio recordings into clear and consistent portions using Labrosa's library effect split function, which automatically detects the extracting non-silent intervals. This step ensures that only meaningful speech data is retained, eliminating silence in the data. I then extracted essential audio features such as MFCCs, spectral centroids, spectral roll-off, zero crossing rate, RMS energy and tempo for audio data in analysis. To simplify the high-dimensional feature set and make the model more computationally efficient, I applied principal component analysis, or PCA, which is a dimensionally reduction technique. PCA transforms the original features such as MFCCs and spectral centroids into a new set of components that capture the maximum possible variance in the data. By retaining only the top components that explain 99% of the total variance, I was able to reduce the feature set down to just 3 principal components, significantly streamlining the input to my classifiers. I evaluated several classification methods to determine the most effective model for speaker identification. These include traditional machine learning algorithms like support vector machines, which find optimal boundaries between classes, random forest, which builds an ensemble of decision trees to make robust predictions, and k-nearest neighbor, or KNN, a simple but powerful method that classifies based on similarities to nearby data points. In addition to these classical approaches, I implemented a lightweight convolutional neural network, or CNN, which, unlike larger, deep CNNs commonly used in image processing, a lightweight CNN is a streamlined neural network with fewer layers and parameters, specifically designated to reduce computational load while still capturing essential patterns in the data. In my case, the input to the CNN was reshaped versions of the PCA reduced features, formatted like a single-channel feature map. This architecture allows the CNN to learn local features, interactions and speaker-specific signatures, even with limited training data. Here you can see the cross-validation accuracy results from all the models tested. Random Forest achieved the best overall performance with a mean accuracy of 41.1% and a standard deviation of 10.3%, suggesting a strong and relatively stable model. The lightweight CNN followed closely with a mean accuracy of 37.8%, showing promising results despite a slightly higher variability. K-nearest neighbor reached 28.9% and the support vector machine had the lowest performance of 18.9%. The confusion matrix for the CNN model reveals a detailed picture of how well individual speakers were identified. We observed perfect classification performance for several speakers, including speaker D, F, S, M, TP and WD, where all test samples were correctly predicted. This indicates the model's strength in distinguishing certain vocal profiles. However, the matrix also highlights some systematic misclassifications. For example, speaker BJ was often confused with BP. To further validate the speaker separability observed in the classification results, I performed hierarchy clustering and visualized the outcome using the dendrogram. Each leaf node represents a speaker sample, and the branches illustrate how closely related those samples are based on their acoustic features. The structure of the dendrogram reveals 2 dominant clusters, suggesting the presence of broader vocal groupings among the speakers. To explore an end-to-end approach, I trained a deep CNN directly on 128 by T-log-mel spectrograms, but it required a pro-level Google Colab hardware, tiny batches, and structured audio windows. As a result, it massively overfit and achieved near-random metrics with a precision of only 0.003. So it was omitted from the main pipeline. This confirms that for our moderate scale data, the MFCC features yield far more reliable speaker separability for the small dataset. Random Forest emerged as the strongest performer among the classical models, while the lightweight CNN showed promising results with improved ranking capabilities and deeper pattern recognition. The confusion matrix revealed both clear successes and consistent challenges among acoustic similar voices. Additionally, hierarchical clustering used a dendrogram confirmed that some speakers form natural groupings based on vocal similarity. Looking ahead, there is great potential to improve the system by introducing data augmentation techniques like experimenting with more expressive embeddings like X factors and implementing higher batch spectrogram-based CNN models. These enhancements would help addressing misclassification and increase overall accuracy, especially for challenging speaker pairs. Thank you for listening.